Computing area is an essential part of calculus, but what does it have to do with an antiderivative? To answer that, let's first try to figure out how we would find the area under the curve of the function f of x. Instead of finding the area of this whole region, let's create a function that we'll call a of x, which will output the area between the bound x equals 0 and x equals the input to the area function. So if this is the line x equals 1, then a of 1 would be the area enclosed in this region right here. We know that a of 0 is the area from x equals 0 to the input, which is 0. Therefore, a of 0 has to equal 0 because there is no width or distance between the x boundaries. So we can plot that point on our graph at x equals 0, a of 0 is going to be 0. From there, we know that the area function will increase because as x gets bigger, there will be more area between the bounds 0 and x. However, we still need to figure out the rate at which the area function increases. We know that the rate is going to depend on the value of the function f, because the bigger the value of f is, the more area will be encompassed as x increases. To illustrate that, let's say we had another function g, which will be greater than f. Since the function g is bigger than f, the area function g will have to grow at a faster rate than the area function for x, because clearly, as x increases, more area is encompassed under the graph of g than under the graph of f. To know the exact rate, let's look at a rectangle with a width x and a height y. And so the area of this rectangle we'll just call A, and it's just x times y. If the width of the rectangle changes by an amount that we'll call delta x, then we'll also get a change in area, which we'll call delta A. Delta A is going to equal y times the change in x, or delta x. So if we rearrange this, then we see that delta A divided by delta x equals y. In other words, the change in area with respect to the change in x is just y. Now if we go back, we can use the same principle from the rectangle example. The rate at which the area changes with respect to x is the value of the function f. The only thing different about this than the rectangle example is that the value of f changes while the height of the rectangle stayed constant in the previous example. So dA dx will continually be changing to match the value of the function f. Now looking at our area function, we can see that its slope at a specific value of x is going to equal the value of x with that x input. So if we want to try to somewhat sketch what this area function is going to look like, we know that at first it's going to have a relatively high slope, and it's going to increase a bit. And then it'll still increase, but it's not going to be increasing as fast, and then it'll increase slower. So our area function will look something like that. To summarize, the derivative of the area function is the function f. So if we want to find the area under the curve of this function, we need to find another function that has this function as its derivative, which is what you do when you integrate a function. But when we find what function has this derivative, we can get an infinite amount of functions. Because if we translate the area function up by 1 unit, it'll still have the same slope at every single point, and therefore it'll also have the same derivative at every single point. So to find the area bounded by one x value and another x value, we need to find the net change of the area on the interval. In this first case we looked at, the change was just the value of the area function because the left bound was at x equals 0, and the area of the function equals 0 at x equals 0 in this case. And the net change between 0 and a final value is just the final value.